Okay, welcome to a rapid session on AC theory. So the first question I have got is looking at this waveform here. What is the peak voltage? So peak voltage amplitude, so it's how high it's going up to. So in this case, it is going up to 2 volts. That is correct. Okay, so RMS voltage. RMS is always less than the peak. Okay, so what have we got from there? Same with any other scenario, we reach for the formula sheet. So RMS voltage equals our peak voltage divided by root 2. So we've got 2 divided by root 2. So there we have it, 1.41 volts. Why do I know that's the right answer? Well, it's less than 2 volts, so we know we're in the right ballpark. So what is the frequency of the sine wave? So frequency is related to time periods, the time it takes to do one cycle. So it doesn't matter where you start as long as you go for, back to the same point. So here to here would be is 800. If we go from here to here, then again that's going to be 800. So that's the time period, and obviously we know that frequency is 1 over time period. So that gives us 1250 hertz, 1.25 kilohertz. Okay, marvelous. Let's have a little bit on transformers then. So a transformer has 120 turns on the primary, 36 volts, output is 12 volts. So we need to know what we've got, how many turns we've got. So let's have a look at the information we've got. So we've got 36, 12. So what is that? Step up, step down? It's a step down transformer. So what does that tell you about the turns? We're going to have less turns on the secondary. So again, we've got a clue in if we're knowing that going in the right ballpark. So let's put the information we've got into the formula. So V1 over V2 is equal to N1 over N2. Okay, so we know that we've got 36 over 12 is equal to 120 over N2. Marvellous. So there we have it. So we've got 3 is equal to 120 over N2. So let's make N2 the subject of the formula so we can swap these two round. So 120 divided by 3, there we go, is 40. And if you want to backwards work it, you can see, but we were always looking for less turns, weren't we, on this secondary? So we know we've got in the right ballpark. Excellent. So let's have a look at an inductance question. So an inductance is just a coil of wire, and we want to know the value of that inductor. What do we know? So we know the current in the circuit, we know the voltage, which means the first thing that we can work out then is the overall impedance of the circuit, which is the same as resistance. So Z is equal to voltage divided by current. So we've got 24 volts divided by 7 amps. So we give ourselves 3.4 ohms. I thought I'd gone the wrong, doing something wrong, different. Okay, so that's what we've worked out is effectively the equivalent resistance of this circuit. So as we're dealing with impedance, so we also know that now Z, from our formula sheet, Z is equal to the square root of R squared plus XL squared. Okay, so if we want to make we're looking to find the inductor value, so we're going to make that the subject of the formula. So we know that XL squared is equal to Z squared minus R squared. Hello folks, back again. So slight boo-boo on my question. We all make mistakes, so that should actually only be 3 ohms there. Okay, so there we go. All right, everybody happy with that? So otherwise we're into dangerous territory here. So let's work that out. So just working that out. So 3.4 squared minus 3 squared equals 2.56. Remembering that that's XL squared, so square root it gives us 1.6 ohms for our inductor. Right, where we're going to take this now? Well, we know that XL from our formula sheet is equal to 2 pi FL. So we can either pop all the information in directly, or we can just make L the subject of the formula if we want. So popping it all subject to the formula, so 1.6 over 2 pi and 50 hertz gives us 5.09 times 10 to the minus 3 henries. Okay, so 5.09 millihenries. Marvelous.